Hello, and in this video we'll take a look at A-level physics, specifically for EDEXCEL. We'll take a look at the absorption and emission spectrum in this video, and also how to calculate the frequency of radiation between energy levels. So specification point 96 states that we need to understand atomic line spectra in terms of transitions between discrete energy levels, and understand how to calculate the frequency of radiation that could be emitted or absorbed in a transition between energy levels. So for this we'll consider the Bohrs model of the atom, which states that it is a system of a small, dense, positively charged nucleus surrounded by negatively charged orbiting electrons. And in this model the energy states are said to be quantized, and quantized by definition means to restrict to one of a set of values characterized by quantum numbers. And electrons can move up and down energy levels by absorption or emission of photons. And this given model can also be used to explain the production of spectral lines produced by individual atoms. So let's take the following hydrogen atom as a given example. At room temperature, the hydrogen atom is in its ground state, which is represented by n equals 1, with n being the principal quantum number. So if the temperature is increased, the electron may gain enough energy to move up orbitals. And once the electron is in an excited state, it can move back down to a lower energy level by emitting a photon. And these emitted photons correspond to a particular wavelength which produce the observed spectral lines. So taking a look at the absorption spectrum, we have a given sample, for example cool gas, and this cool gas is applied with white light. Now using a diffraction grating or a prism, white light can be split up, and there will be gaps present in the absorption spectrum, and these gaps correspond to the wavelengths of absorbed light which have been absorbed by the electrons within the gas atom. So this results in the electron excitation, meaning that electrons will actually move up energy levels, and this shows as a series of black lines in a continuous spectrum, and this is defined as a line absorption spectrum. Taking a look at the emission spectrum, let's just say we have another given sample. Let's just take gas again, and this time it's applied with either heat or light. So this causes the excitation of atoms, therefore electrons move from a lower to a higher energy level, and this causes the atom to become unstable. Therefore an electron has to emit a photon returning from a higher to a lower energy level. And using a diffraction grating or a prism, white light from the hot gas can be split up, and in the process the wavelengths of the emitted photons show up against a black background, and this is known as a line emission spectrum. Now here we are represented with a following question, which states that a diagram shows the lowest energy levels for a certain atom. And it says a photon with energy 3.9 electron volts is absorbed, so an electron can move from, and then here we are given a series of options to select from. So to determine the answer for this question, we have to use the energy difference formula, which is represented by the change in E, which gives the energy difference of 3.9 electron volts. So we have to consider which two energy levels actually provide the energy difference of 3.9 electron volts. So for this, in this case, it would be the fourth energy level in the ground state. So we work out the energy difference by using the fourth energy level, which is negative 1.6 electron volts, and we subtract that by minus 5.5 electron volts, and as we all know, two negatives make a positive, and that gives an energy difference of 3.9 electron volts. So therefore we can deduce by this that it'll be option B. So the electron could move from the ground state to the fourth energy level with a photon energy of 3.9 electron volts. Now moving on, we are represented with another set of questions. So question 1 states that an electron is accelerated through a potential difference of 12.75 volts. How much kinetic energy has it gained in electron volts and also in joules? So for this, we can equate kinetic energy and electron volts together, and therefore we can express the answer as 12.75 electron volts. And this is going back to that definition of the electron volt, which states that it is the kinetic energy acquired by an electron when it is accelerated through a potential difference of 1 volt. So therefore, that's why these two formulas can be equated, and the answer can be expressed as 12.75 electron volts. Now to change electron volts into joules, we have to multiply 12.75 by the following value of 1.602 times 10 to the minus 19 coulombs, which is the charge of an electron. And we end up with an answer of 2.04 times 10 to the 18 joules. We go back. The next question states that this electron hits a hydrogen atom in its ground state and excites it. Explain what is meant by excitation. So basically, excitation is the absorption of a photon by an electron, resulting in the electron moving to a higher energy level. And if we go back, using the energy values on the right, calculate which energy level the electron from the hydrogen atom is excited to. So as we already know, the electron is already in its ground state, and we have to find out to which energy level it actually goes to. So for this, we actually have to work out the energy difference, which provides an answer of 12.75 electron volts, as the energy acquired when it is accelerated through that voltage is 12.75. So for this case, I considered using the fourth energy level, and I subtracted that by the ground state energy. So I got negative 0.85, and I subtracted that by minus 13.6, and I got an answer of 12.75 electron volts. So basically, the electron that's in the ground state actually can jump up to the fourth energy level. And then for the third part, it states that I need to calculate the energies, or all the energies and frequencies of all photons that might be emitted as the electron returns to its ground state. So for this, I have to consider all possibilities of a photon emission from the different energy levels. So I have to consider the emission of a photon from the fourth to the third energy level, from the fourth to the second, and also from the fourth to the ground state. And I also have to consider this from the third energy level to the second energy level, and also from the third to the ground state, and then from the second energy level to the ground state. So I use E equals hf, which is basically the photon energy equation. I rearrange to make F the subject of the formula. I then use the photon energy difference formula, and I find the difference of energies between the given energy levels. So for example, for the first one, the difference in energies is given as 0.65 electron volts. I then convert those electron volts into joules by multiplying it by 1.602 times 10 to the minus 19. I then divide that by Planck's constant, which is given as 6.63 times 10 to the negative 34. And I end up with a value of 1.57 times 10 to the 14 hertz for the frequency. And that is the frequency of radiation that is emitted from the fourth to the third energy level. And also looking at the second one, it follows the exact same rule. So we use E equals hf. We rearrange to make F the subject of the formula. I find the difference in energies between the fourth and the second energy level, which is 2.55 electron volts. I convert those electron volts into joules, and I end up with an answer of 6.16 times 10 to the 14 hertz from the fourth to the second energy level. And this third one follows the exact same procedure, and also the next three the exact same way as well. Thank you all for watching. I hope this video has made sense and cleared any questions anyone's had regarding the absorption and emission spectrum, and also calculating the frequency of radiation between energy levels. Thank you all for watching, and goodbye.